Hey guys, in this video I'm going to introduce the Freebody diagram. This is a helping tool to help you solve Newton's second law correctly. It's not a necessary requirement that you do a Freebody diagram for every Newton's second law problem, but it's a huge help for you to identify problems that you've missed and forces that you haven't identified correctly, whether you get the right acceleration. It's really a great way to help you solve Newton's second law problems.
Specifically, free body diagrams help you find the sum of all the forces. It helps you identify what forces are acting on the object, how they're acting, and how you're going to add them up to find the force. Of course, the goal is to find the acceleration. So the free body diagram helps you find the acceleration, but it also gives you good intuition for it. So you can sometimes check to see if your acceleration is obviously wrong. And so you need to go back and try to solve the Newton's second law problem again. So there are three basic steps to drawing a good free body diagram. First one is to draw a rough sketch. That's just a good practice for any physics problem, but we need it to be good for a free body diagram as well. Then add arrows to your sketch to represent all the forces which you expect to find in this situation. And then maybe the most important step is to check the resulting acceleration against your intuition. If you know the object is not supposed to be accelerating, your free body diagram should not show the object accelerating. So I'm going to do this for a specific example. The example I want to do is skiing down a hill. First thing I need to do is get a rough sketch of someone going down a hill on skis. Okay, so there's a rough sketch of someone going down a hill, and then I need to add arrows to the sketch that represent forces. So the first thing I need to do is I need to decide where on this skier are the forces acting. I have basically two options. I can make all the forces act at the center of mass of the object. For this skier, the center of mass would be something like right in his chest or something. Or you can make all the forces act at the correct locations. So which one of these you pick depends on how you're modeling your objects. If you're modeling your objects as points, which is sort of the first thing you do in physics, then the objects just represent points, and all the forces that act at the center of mass, that's the only location on the object at which they can act. So typically you will start by making all the forces act at the center of mass. Now as we go along in the semester, we're going to start to consider objects not as just points, but as real extended objects. This person, for instance, would have skis, he would have legs and a head and such like that. So then you would want to make all the forces act at the correct location. Because, for instance, the gravitational force is definitely acting at the center of mass, but the friction force between the hill and the skis is definitely acting right here on the skis. And when you want to consider objects that might do more than just translate in one direction, they might rotate, you need to take into account the fact that forces don't always act exactly at the center of mass. But for now, we're just going to start by having all the forces act at the center of mass on this skier. So what forces do I expect? Well, I certainly expect a gravitational force because this is a person and they have a mass. So I'm just going to put my gravitational force on this guy starting at the center of mass. Gravity is always pointed downwards, and I'm going to make the arrow about like that. So we can usually say, okay, we know there's a force of gravity, so put the force of gravity on the diagram. That will always go from the center of mass regardless of which of these two options I pick, but I'm going to make all my forces act at the center of mass, so it's going to act right there. Okay, so I also mentioned that there might be some friction between the hill and the person. Of course, this is snow, so there's likely not very much friction, but there could be some. So let's put the frictional force on there. We haven't studied too much about friction yet, but it should be very intuitive to write the friction force in that way. Going backwards, the opposite direction the person is moving. Later we'll learn that friction always acts parallel to surfaces and always opposes motion. For now, it should be pretty intuitive that that's where friction should go. So are we done? Are there any other forces that we can think of? Well, let's say that I'm ignoring air drag, so there's no air drag on this person. But what I can't ignore is what the hill is doing. So if the hill wasn't there, this person would just plummet straight towards the earth, regardless of what friction was doing, right? So the hill is obviously doing something like holding up the skier. That's called a normal force. So normal forces always act parallel to surfaces. Therefore, the normal force from the hill will be acting in that direction right there. And I'll label that Fn. So now I have to say, okay, are there any other forces that I think should be on here? If I can't identify any of them, then the next thing to go on is to go to step 3 and check to see if these forces give me the acceleration that I expect. Now I might not know much about what the acceleration of this guy going down the hill is, but I certainly expect it to be along the hill in the direction of the motion of the skier, or possibly 0, but I shouldn't be able to add up all these forces and get an acceleration, which is somehow directed off the hill or into the hill, right? And so I can check this because I have graphical representations of these forces. I have these arrows, which I can add together using my graphical vector skills, and determine if I get an acceleration, which actually is something like what I expect. So the first thing I'm going to do is I'm going to redraw the force of gravity over to the side, and I'm going to try to keep it about the exact same length and direction as my actual free body diagram has it. All right, so there's my force of gravity. Now what I want to do is I want to take my force of friction and move it over here. I'm going to move it right here because they have to be added head to tail because that's how you add vectors. So let me just put him right there. Okay, so now I want to do the last one, which is the normal force. Take the normal force, move it head to tail with this force. So it should be pointed up in that direction. Try to make it about the same length as the normal force I have. That seems to be about right to me. So you can see what I did is I added them all head to tail. Here's the tail of the gravitational force down to the head, tail of the frictional force, tail of the normal force up to the head. So that means the sum of these, that plus that plus that, is this little piece right there. So that little piece we can call the sum of all the forces. We can call that F net if we want. They mean the same thing. But that little arrow shows the sum of all the forces, the net force. So the direction of this thing should be the same direction as the acceleration. So that means the acceleration is directed down the hill, as we expect. So I think that I haven't forgotten any forces because the acceleration is exactly what I expected. Let's say that I had forgotten a force. Let's say that I had not included the normal force. If I did this diagram without the normal force, I would have made one arrow for the gravitational force, I would have made one arrow for the frictional force, and then I would have said, okay, what's the net force there? Well, the net force starts at the gravitational force and then has to go down to the head of the frictional force. That's F net. That's in the same direction as the acceleration, so apparently this skier is accelerating into the hill. That's obviously incorrect, right? It can't be accelerating into the hill because we know he's not. So that means I've forgotten a force. This guy is wrong. I've forgotten a force, and I should go back and try to remember all my forces and then remember that there has to be a normal force because the hill is pushing up on the skier, and then I should get back here. So every one of these steps is extremely important to getting the right free body diagram. The last thing I want to say about making free body diagrams is that notice that although my skier might have some velocity, it might have some acceleration, I did not include that on my free body diagram. So in this second step, when I say add arrows to your sketch to represent forces, I really mean only forces. You don't want to start adding things like velocities, things like accelerations into your free body diagram because then that might confuse you when you try to add up all the forces. You might add a force, a force, a force, and an acceleration or a velocity or something else, which will distract from your solving of Newton's second law. Newton's second law cares only about forces, and so only forces should be put on your diagram. Of course, I wouldn't mark you wrong or anything if you put an acceleration or velocity on your free body diagram. It's just good practice to not do it because you might make a mistake. Okay, great. So that's an introduction to free body diagrams. I hope this makes sense. We're going to be using these all the time in the next few weeks to solve Newton's second law. Thanks very much, and I will see you guys in class.